Good morning. Um, let's continue where we ended yesterday. So we have seen that neutrinos indeed do oscillate. They can change their flavor. So we have computed as example this transition probability, and we have seen that this is in general. It depends on the mixing angle, depends on the mass square difference, depends on the distance, depends on the energy that the neutrinos have, but in general, this is non-zero. So, which means we have seen that individual lepton number for the electron is violated. Also for the muon is violated. If you include, or better to say the delta, so there's a transition which changes it. Now here we would have delta L tau, which is 0. But if you look at a transition of a mu neutrino to a tau neutrino, you would find that also this individual lepton number is violated, right? So you would have before, you just have L mu equals to 1, L tau equals to 0. And in the end, you have L mu, which is 0, but you will have an L tau, which is 1. So also there you would have a delta, which is non-zero. So we know that the individual lepton numbers are violated. As we said yesterday, if we look at what is the delta L, so we sum up the individual lepton numbers to end up with the total lepton number, we always see for neutrino oscillations, delta L is equal to 0. So neutrino oscillations don't change the total lepton number, right? So this all we have done for neutrino oscillations. Now the next question you can ask, or the next curiosity you can have is, but okay, neutrinos do oscillate. Do also charged leptons oscillate? So this is what, is there also something where I can have an electron that kind of oscillates to a muon or something like that? This, just to say, are there charged lepton oscillations? The short answer, as I said already yesterday, it's no. There is a very nice article written by Evgeny Akhmedov. Which has the archive number 0706.1216, where this question is answered, and the answer is no. I will not discuss this more in detail, but the answer is really charged lepton oscillations. You will not see, this is not going to happen, and this is nicely discussed there, and I think it's accessible also to you with the knowledge which you have already. So the next point is, however, what one can ask. So, okay, even if charged leptons don't do exactly the same as what neutrinos do, they don't oscillate. But are there processes with, let's say, delta Le non-zero, delta L mu non-zero for charged leptons? So this is not an oscillation, but maybe it's a decay. And probably the most prominent example of this you see in this little cartoon over there. So this is an anti-muon decaying to a positron and a photon. So again, so we would start with L mu, which is -1 because it's an antiparticle. Le is is 0. The end, you would have mu being 0. The photon doesn't have any lepton number. And you would end up with Le minus 1. This process, in principle, is allowed. I mean, you should ask yourself, why doesn't this happen? The mass of the muon is around 106 MeV. The mass of the electron is just half a MeV. The photon is massless, as you know, so kinematically, this is allowed. This channel is open. We also do not break any of the gauge symmetries, which we know, which are there at very low energies. We do not break color because none of these particles are colored. And electric charge is also conserved because we start with a positively charged particle, and in the end, the overall charge of the final states is also just +1. So the positron has charge +1, the photon has no electric charge. So the question is, this one, if you have followed some lecture about standard model, and for sure you have sometime, is never discussed because in the standard model, this process does not occur. So in the standard model, the branching ratio for this process is 0. Where the definition of the branching ratio, which is commonly used, is you take the decay width to exactly this channel and divide it by the most dominant one, which would be, now let's do plus E plus to have the everything in order, E plus nu E nu mu bar. Yeah. So now the point you can ask is, so now in the standard model, you will find there's no way of getting this. But what happens anytime when I go beyond the standard model? So now it means in the standard model plus neutrino masses. So we know we need neutrino masses because we need to describe correctly the observations, in particular of neutrino oscillations. What happens here? So we do not yet specify the exact mechanism in the way we want to generate the neutrino masses. We just say we assume, so we have the standard model and we have something which generates neutrino masses for us. Also, it's not relevant, notice that they are generated as Dirac particles or Majorana particles, just neutrino masses. And then you ask this question, you ask yourself, what happens? You find the answer over here. So this is the diagram, which actually is an example of giving you mu2 gamma. Because you see, you start with a muon. In the end, you have an electron and you have a photon. What is inside this diagram, how to understand this diagram is, here you start with actually a right-handed muon. Then you have what is called a mass insertion, which does a chirality flip. So it flips from a right-handed muon to a left-handed one. Why do you need to flip to a left-handed particle here before the loop comes? Exactly. If you want to interact with the W boson, everyone needs to be left-handed. So you have to have at this vertex a mu L, which comes together with a nu L, one neutrino of some left-handed type. Here we have left-handed neutrinos. And then, so however, what is sitting here at the vertex, this is what we discussed at length yesterday, actually is sitting the PM&S matrix. So here you see the PM&S matrix, the element which you need. Actually, you need the transition between a muon and a neutrino of the flavor mu, but you express this muon of the flavor mu, you express in the mass eigenstates, which we got to know, the nu1, nu2, nu3. So which explains you why you get this the vertex. Then you have the loop, where you have the W boson and the neutrino as mass eigenstate running. Where does the photon come in? In this loop here, obviously a photon which relies on interaction with electrically charged particles can only couple to the W boson. The neutrino is chargeless. And then we have to close the loop here. What can we do? Again, we write the nu I in terms of the electron neutrino flavor, which gives us this this coupling here, this element of the PMNS. And what can we couple it to? To a left-handed electron. So this is the way in which we close the loop here. This is a computation. If you want to find the details of this computation, you find it, for example, in the book by Sheng and Li. But we're not dive into this computation because even though it's a one loop process, it would be filling at least one lecture to do this computation. However, I would like to present you the result of the computation, and I would like to discuss with you briefly the main characteristics. Okay? So we have this branching ratio. How does this look like? Alpha 32 pi. There is a K which runs over 1, 2, 3. Then I get the mu K star k m mu K square and W square. And this is all squared. So, or let's simplify this. This is MK, where MK is either M1, M2, or M3. These are the neutrino masses. So just to understand why this result makes sense. So you first have an alpha here. This encodes the coupling strength of the photon because this is the fine structure constant. This explains you the vertex over here, which you get if you square it. You do get some loop suppression. This is like this relic here is this 32 pi. And then you see the expression that we were saying. You see that there's this vertex, which we had before. The vertex here to the left, you have the vertex to the right. You have the effect of having the neutrinos in the loop. This is corresponding to their mass. And you have obviously the mass of the other particle which runs in the loop, which is the W boson. So there are two characteristics of this, actually. So the first characteristic is that this one is the leading term, so it's the most dominant term, because we have the unitarity of the PMNS matrix. So what is the point? If you assume there was not this weighting factor with the mass of the light neutrinos, so we would have the sum 1, 2, 3, U mu K star, U E K. So what's this? So I write it differently. This is actually, so you can write it as U K mu dagger. Then you sum over K1, 2, 3. Mu K Oh, EK, sorry. Okay. So do you see this now better? What is this? Everyone. This is just mathematics. This is not even physics. Hmm? So this would be like, this is a matrix. So this is usually like you do a matrix product. This would be U dagger, okay? Because you have to sum over, one is the column, the other is the row. But we don't want to get the entire matrix, we just want to get one element. And we get the element which is called E mu. This would be the element which is 1, 2, okay? What did we say? Here's written for your notation. So the PMNS matrix is unitary. So what do we know then about this product with U dagger? What is U dagger? Must be the identity matrix. So we have here the identity matrix, and you have to evaluate the 1, 2 element of the identity matrix. So it's 1, 1, 1, 0, 0, 0, 0, 0. So the 1, 2 element is 0. Is this clear? Good. So, which means this is a mechanism which is known since long time in quark physics, and it takes the name of GIM mechanism. Did you hear about the GIM? So the GIM mechanism tells you that the leading order term, which actually would not have any suppression from masses, is 0 because your mixing is unitary. And this is what we also observe here. So otherwise we would have really an extremely strong effect. But the BMNS is unitary, like the CKM matrix. And so we lose the first term, and we get this as dominant term. So now you are already experts in the masses for neutrinos. So let's say we are conservative and say that what we see, this MK, we are nice, is for sure it's smaller than 1 electron volt. What's the mass of the W boson? Roughly. Huh? 80 GeV. I mean, 100 GeV would be also okay if you tell me this. I mean, it's a weak boson. So is the W and the Z, they're both weak bosons. They get the mass through the electric symmetry breaking. We know that the electric scale is something like 170 or 200 JeV. So we expect that the mass, which is associated for the gauge bosons, due to this breaking, is roughly the order of the electric scale. So the W boson has the mass of 80 GeV. So what's the ratio then of Mk over Mw? Just order of magnitude wise. So it's 1 electron volt over 100 GeV, which means we have, this is 10 to the 2, 10 to the 11. So we have 10 to minus 11, roughly. Being generous, 10 to minus 11. So this we need to have at the 4th power, because we have here Mk square over Mw square. And this you square yet another time. Okay, so what's the size of the branching ratio then? The size of this branching ratio, which you can estimate, even without doing this computation in any detail, you see, in the end, taking into account the other factors, is for surely smaller than 10 to minus 50 in the standard model with the light neutrino masses. Okay, just telling you that introducing light neutrino masses just to explain the neutrino oscillations which we observe. What does this do to the individual lepton number violation which we see among the charged leptons? It introduces a very small effect. Just generic. So the minimum is, this is tiny. Is this clear? So now the other question you can ask, what are the experimental limits currently? Do you have any idea what are the experimental limits on this process? exactly. And for this, generations of experimental physicists worked very hard, in particular at the PSI in Switzerland, to reach. So the last limit which you can get is 3.1 times 10 to minus 13. This is the experimental limit at 90% confidence level. So coming from an experiment which is called MAC2, taking place at PSI in Willingen in Switzerland. So which tells you that you're not destroying anything drastically by just introducing light neutrino masses which violate the individual lepton numbers, because you are not changing completely the world for the charged leptons, which would be really a huge problem. I mean, this would make everything crawl, because we have this limit. This limit is actually, as a friend of mine in this collaboration, she insists in saying, this is the strongest limit which you have on the branching ratio of a decay. It's the world's strongest limit on any kind of decay which you have. So, I mean, they really do amazing work, okay? So, but they are many, many orders of magnitude away from what the expectation is if you just throw in light neutrino masses. I want to say two things very briefly. Point number one is, if you obviously have a particular mechanism in mind to generate neutrino masses, or other physics beyond the standard model, like for example, supersymmetry in the incarnation of the minimal supersymmetric standard model, or many extensions of the standard model, which do a good job because they give you, for example, dark matter candidate or whatever. These easily can be orders of magnitude larger. And in principle, you have a lot of theories beyond the standard model where this constraint is really a very strong constraint on your theory. So just to say, it's not that what they do is a hopeless job. I mean, they are actually constraining many also of my models, which I constructed and looked at and studied. They constrain this heavily already. The second comment is that you don't have only this process. You also have a process which is called, in its short words, mu to 3e. So you're not breaking electric charge still, but you could do the following. You would have, that's what not the same experiment, but the similar experiment is searching for. You could have a mu plus, which decays to an e plus, e minus, and e plus. This is called mu to 3e. Momentarily, you can also have this as variation with a tau lepton, which decays to this, or, I mean, since you have a muon, you can only decay to electron positron. But if you have a tau, you could say, okay, for a tau, I can decay to mu plus, e minus, mu plus combination. I could also decay for a tau to something e plus, mu minus, or things like that. No, you have more options. This is also searched for. This one is going to be searched for again at an experiment called mu 3e. It's going to run very soon, in the next year, hopefully. And these ones are usually searched for at experiments like Bell 2. Some is also done at LHCb. I explicitly put this on the blackboard because you will have a nice exercise, I hope, with Joao, where you will see some of these processes, and you will see how actually you can, while having a mechanism which generates neutrino masses for you, you also get these processes for free, so to say. Okay. And these are not the only ones. There's also something which is called mu-E conversion in nuclei. there are other type of experiments that are actually testing this. So you are always, people are eagerly, in particular in the recent past, set up new experiments that they are really searching for the violation of individual lepton number, also among the charged leptons. Because we have so solid evidence for this among neutrinos, and many extensions of the standard model give you huge signals. So it makes perfectly sense that this is searched for heavily experimentally. Do we have any questions regarding this? Yes, please. Okay, so but you have here the neutrinos, they are propagating. So in principle, you write the propagator of a fermion. You know what the propagator of the fermion is. It would be p slash minus m. And then usually you do the stuff when you write down this, the gamma algebra and stuff, then you would end up with a p slash plus m divided by p square minus m square. And there's this m coming from. You see what I mean? It comes out of the calculation here. Let's see. And this dominant part here actually is also the dominant part from the loop. Mm-hmm. Ah, you mean the one here? Ah, okay. Sorry, I misunderstood. So, why do you need it here? If you write down, so how would you actually write down mu T gamma in, okay, maybe this leads too far, mu T gamma in an effective T. I mean, you understand if you were starting with a left-handed one here, you would get 0, right? If you start here left, then you do right, and then, okay, exactly. So, or maybe I do it. So you have to stop me if this is too crazy. So what's the actually in effective field theory actually giving me this diagram? What is this operator? So you would have to have a charged lepton, another charged lepton, and a photon. So you would say I take an A mu. Okay. I mean, just to write it down in terms of term which I can put in the Lagrangian, right? Actually, it's not going that you this way, because then you would have left, because you know that currents are going to be left. It's not going to be this way. It's going to be through the field strength tensor. This is this beast. Now this gets more specific, is the field strength tensor. So now you have F mu nu. F mu nu, you beat up here by sigma mu nu. Sigma mu nu, usually you're not coming across this Lorentz structure very often if you are studying just beginning of QFT. But sigma mu nu is something like the commutator of gamma mu, gamma nu. Okay, 2 gamma matrices. Okay, but if you have 2 gamma matrices, you're not going from L to L because this gives you 0. You are going from L to R or R to L. You have to have this flip. Otherwise, this diagram is even not existing. So, and then you only have to decide, where do I put this flip? Do I put this rather on the muon or on the electron? Okay. If you put it on the electron, also this contribution exists. But then you have a suppression with the electron mass. You're not coming with a muon mass, so you take the largest mass. So this was, sorry, I mean, if not everyone could follow, this was more specific than I thought, and this is already very detailed, but just to give you a feeling of why this is always going to be a transition from L to R or R to L. Okay, very good. Do we have more questions? Yes. Sure. Sure. Of course. You are absolutely right. Thanks a lot for the question. Yes. So, okay, there are two things to it. So we are coming now to how to generate light neutrino masses. If you think about what we call the vanilla type 1 seesaw, where you put heavy right neutrinos, and if you have seen the name seesaw says like make the heavy guy heavier and the light guy becomes even lighter, right? But you are kind of at a certain point you are paying a price because you made you made the mass so heavy, but the coupling is order 1, then you will get this huge suppression in here. It's not the diagram structure is different in the sense that you are going to now pay a price. You still have to couple to a W boson, right? You don't get, I don't know, as present another gauge boson, right? You would get, you would still have to go with the W boson. The W boson, but really just wants to speak to left-handed particles. So if you have a right-hand neutrino, you first have to go through the conversion of, and this is suppressed with a light neutrino mass. So usually if you have vanilla type 1 seesaw, the heavy guys are extremely heavy, you have order 1 Yukawa couplings, then this is negligible. Again, but if you have something which is like low-scale seesaw, where you need some additional symmetries to be arranged, that the heavy guys are not as heavy as you think, and the couplings are still pretty large, we are in business. And this is constraining. Okay, you're welcome. Other questions? If not, I would say, let's leave this, and we are going to go to how to generate masses for our neutrinos. So you're already expert in the sense that you already know some way at least of doing it. No, here it is. So always keep in mind, have this picture in front of your eyes. So the current knowledge is we have 3 neutrinos, and definitely 2 of them have mass. The third one maybe does what it does, and we don't know. So, and we come back to the easiest extension which we were thinking about. The easiest extension was, now we generate neutrino masses. So think back to what we did in the beginning, would be we take standard model plus right-handed neutrinos, and at least we have 2 of them. That's what we were saying. So then I write down the immediately boring Lagrangian. You remember what we saw? This is are the left-handed lepton doublets, which continue left. These are the right-hand neutrinos now. This is the Higgs field twiddle, so the charge conjugate, and this is the Yukawa coupling matrix, right? Okay, so, and we were saying, okay, this will give us some masses, called this always M nu D, which is going to be this funny matrix, and square root of 2, the VEF, so which comes just from this one. Now, with the knowledge of what the size of the light neutrino masses is, we would like to make an estimate of the size of the Yukawa couplings which we need. So how big are the elements of this matrix? If there's nothing special happening, so always no special symmetry or whatever. So light neutrino masses. smaller than 1 electron volt. What is the typical scale of V over square root of 2? We already had it today. What's the electric scale? I mean, let's be generous. We say just 200 Jeff. So that's the electric scale. Then we have this Yukawa coupling, and we should get something which is smaller than 1 electron volt. How do we do this? This one is going to be something small. 200 Jeff is 2 times 10 to the 11 electron volt. So this one is going to be 10 to minus 12. So compare this, please, to the next lightest fermion, which we know. The next lightest fermion, obviously, is a charged one. This is the electron. The mass of the electron, we already had this also today, is roughly 0.5 mega electron volt. So this one then gets a Yukawa coupling, which is around 10 to minus 6. So you still have a few orders of magnitude more for the neutrinos. Okay. There are now two things. The first thing is like, you would say like, but really I don't like this small number. I really don't like it. Because, I mean, it's orders of magnitude smaller than this electron, and why should it be so small? I mean, I want like to understand why neutrinos are so light. Not by just putting in the right number. That's the first point. Then there's the point of saying like, let's think back. Maybe neutrinos are really Majorana. If they're Majorana, maybe we can actually get their masses in a different way, right? That's the next point you can think about. And then you can ask also a question, okay, if you can live with this number, would you run into theoretical problems? So, I mean, if you have had a class on standard model and QFT, maybe you discussed this. Would you run into theory problems with such a small coupling for a fermion? Not for a scalar, but for a fermion. Would this be a problem? Actually, from someone who does only QFT and is interested in whether the theory can be consistent or not, or is fine-tuned or has some defects, the answer is this number as a small coupling for fermion is perfectly fine, is legitimate. Because if you renormalize your theory, this coupling would stay that small. So that's okay. So in that sense to say, the point that we don't like this small number is first of all like an aesthetical point that we say like, maybe this small number wants to tell us something. And then it's coming in addition that we always remember that neutrinos are the only ones that could be in principle Majorana. So, and that's what we want to explore. But someone who is happy with this and likes it and is okay with this is also fine. But then neutrinos are Dirac particles, and we don't talk about them that much anymore about neutrinos. I mean, in a different way we can talk, but it's not that what most people think then would talk. Is this clear? So let's say I belong to the theorists which say I don't like this. And I would like to explore possibilities that are often, or very, very often, related to the fact that neutrinos are Majorana particles and ways of generating masses for them by saying they are Majorana. For this, I would like to first take, before coming to a particular mechanism, I would like to take the viewpoint of what is called an effective field theory. So it might be sounding scary, but so you know the standard model. If you learn about the standard model for the first time, what are the special points about the terms which we write in the Lagrangian for the standard model. Can you help me to characterize them? How do you characterize, if you have to explain to an alien the pieces which make up the standard model? So in the Lagrangian, in the standard model, you want to explain to someone, you're allowed to write down this term, but not the other one. What are the guiding principles? Which symmetries? Yes, more symmetries? Yes. Dimensions. So what kind of dimensions? What are we thinking when you said, the you don't write down all terms which you could write down in standard. You write down the ones which are what they're called renormalizable, which have up to mass dimension 4 without introducing new mass scales. However, this is only the beginning. So you could say, let's take the standard model as effective field theory. So standard model as EFT would mean standard model, we still use all the symmetries which you were telling me. But now we are not stopping at mass dimension 4. We go on 5, 6, 7, 8. I mean, people went on quite a bit. But we can be modest. We gone up to 5 only. How many operators do you think you can write down at mass dimension 5? I mean, this has been done already in the 80s when I was just born, but all of you otherwise were not born. Okay, Maura, you were, but the rest was not even thought of, okay? But then people were already considering this. Exactly. So the amazing result is, if you impose standard model, the gauge symmetry is Lorentz symmetry. The only thing which I can write down at dimension 5, at mass dimension 5, is one operator which is in honor of just Steven Weinberg that passed away recently. It's just called the Weinberg operator. So the Weinberg actually is made out of leptons. This is good, left-handed lepton doublets. And so this, we already looked at this in the first lecture, and we said, this one is not good because it has hypercharge, non-zero. You're not allowed to write this down in the standard model. You need to add more stuff. So you can actually add simple stuff. You can add another one Higgs, and then you need a second one. Okay, this is dimension 5 because in the counting of the dimensions in 4 dimensions, a fermion has 3/2, and each scalar has 1. So this gives 5. So now, in order to write this down in your Lagrangian, you are not allowed to write down the dimension 5 in the Lagrangian, because if we think about the action is when you do the integral over d for x, you have to have 4. So what do? We divide by some mass scale, new physics scale. So this is roughly just called, this is the new physics scale. This is a number which is just making the dimensions right. This is not yet, I mean, I've not said yet anything about this. I just said that this is measured in GeV, okay? This is the only thing I say because I want to do the mass dimensions right. And then obviously you have couplings. Let's call them C and J. Because of the structure of the term, these couplings are symmetric in flavor space. And what do you observe here? This is fantastic. This term is gauge invariant, is Lorentz invariant. Obviously, it's also invariant under baryon number. And what about lepton number? Huh? A lepton number exactly is delta L equals to 2. Okay. And if you take the standard model and you just now, you accept this term as the new term there, you make friends with it, you say, okay, I include you, although you are dimension 5. What happens after electric symmetry breaking? So the Higgs and also the twiddle, they get a wave. Which component gets the wave? I don't remember. V square root of 2, 0. This one. So you put this in. You remember that the LL has this form of being a new left, and then you have a charged lepton left. And you calculate, because this is just a matrix product. So you would end up with something which is Cij over lambda, nu L E bar, JC, and you get the V square root of 2. You get it twice. I mean, you square it because you have this one. So what is this? It's a Majorana mass. Okay, so here it is. This is M nu M. And we can read off what's the size. Cij, so this component Ij divided by lambda. Then we have V squared. There would be this factor of 1/2, which I just would pull out because we were talking about this Majorana convention that people usually like to put a factor of 1/2. So you would say, this I make equivalent now to 1/2 nu L bar J M mu Ij. Okay? So far, so good? So again, we have as benchmark point, this should give us light neutrino masses that are smaller than 1 electron volt. So now we do the discussion of the possibilities which we have. What can happen? So, which means, so with this one, we know what V is. We know that this is 200 JeV, roughly. Okay. I was a bit more strict. When I do my estimate, I was saying, let's assume that this is 0.1. So then I learn the following. If I have to hit this number, and I know that V is around 200 GeV, I can calculate what's the constraint on this combination. Okay, the coupling divided by this new mass scale. And what do I find? That this thing should be smaller, equal to 5 times 10 to minus 15, and the unit is 1 over GeV. Okay, so now this is what we are dealing with. This is the benchmark which we have to hit. So this is like when you build your experiment, this is the requirement. Okay, so now this is the theory requirement. And in principle, you can divide the ways to achieve it in 3 different categories. Okay, so there are 3 different, I would say there are 3 different categories for getting this. So there's the category number 1, which I would just call the seesaw category. Category number 1, it says lambda is large. I mean, much, much larger than the electric scale. And these couplings are all around 1. When I say all around 1, I mean, they might also be 0.5 or 2 or whatever, but they are around 1, okay? If I fix myself to this, I say I just want it. I can compute what should I put actually for this lambda. I take my benchmark equation and I put in, and my conclusion is this lambda should be really large. This should be around 2 times 10 to the 14 GeV. So this is where the new physics is going to sit. Any new particle which comes in, which gives me masses for neutrinos, so it's, I mean, in my idea, my prejudice that the couplings are order 1. It sits there. Okay, that's naive prejudice. So this is what, these are all the seesaw mechanisms, the typical ones. Seesaw mechanisms, we have something which is called type 1, we have type 2, we have type 3. Joao, you are discussing with them where I don't write type 4. These would be the seesaw mechanisms, which people invented in the 80s. Okay, and we will talk about them in a second. And these are all based on, you know what the English word seesaw means. So it's the typical picture. This is a seesaw where children play, and you have a heavy new particle. So the lambda is now representing the heavy new particle. And the heavier it gets, the lighter the light neutrinos get. Okay? Because the bigger you make this lambda, the smaller the light neutrino masses you get out. So that's the seesaw. Clear until, yes, please. You have this. These are the light neutrino mass, okay? So at least they're 0.1 electron volt as maximum. So I take this value and I equate it to Cij over lambda times V square. V square is the electric scale. So when I did this, I put in 200 GeV. And then you get this number. Okay, clear? Good. Other questions? If not, we move on to the next possibility in order to hit this benchmark. So the next category. So the next category, I would say, is going to be number 2. So this would say, no, we do it vice versa. Tiny, because of symmetry. I mean, I have some principle which tells me that this should be tiny, and lambda, roughly, let's say, a TeV. Okay? So that's the next idea. So I can turn it around, right? I could say, once I was making the light neutrino masses light, because this lambda is huge, but the coupling is order 1. Now I do it the opposite. I say, let's make the coupling small, but not make it small like for Dirac neutrinos, where just the Y nu is small, but I have no good reason for it. But make it small with a symmetry, okay? Because symmetry, and which is lepton number, has a very tiny breaking. I have to engineer that. So the symmetry usually is actually the U1L, which we have seen. This is lepton number. So I have a very small source of lepton number breaking. And if I can engineer that, I will have the lambda that doesn't need to be that big. It's not that far away from the electric scale. there's hope that this can be even such particles could be produced at LHC or at the future collider. Okay, that's the that's the next idea, so to say. That's the next category. And one example would be something which is actually has the funny name of the inverse seesaw. And then there's the third category. The third category is a mix, which means lambda, so now it's very vague. I say not too big and this one a bit suppressed. So just 10 to minus 5, okay? Bigger equal 10 to minus 5. This is something like we know already as Yukawa coupling from the electron. And we do some mix. So we can, if we make none of the two, neither the enumerator nor the denominator go to extremes, so we can arrange some intermediate situation. So, and that's typically realized in what are called radiative neutrino mass mechanisms. Radiative means you generate them via loop. We are not discussing this in detail. So here's just a nice little picture of now, if you're okay with doing Feynman diagrams. So the first line, you see the type 1, type 2, type 3 seesaw. Then you see here, this is an example of the inverse seesaw, where you see actually this coupling, which is here, this mu s. This is the one which sources this breaking of the lepton number. And this is chosen to be tiny. So this is small. And then you see here the friends which are in the third category. The friends which are in the third category is this loop generation, where these new particles which are going to flow around in the loops, they usually have masses, let's say 10-ish TeV or something. And the couplings which you have at the vertices here, they are not super tiny, but they are neither order 1. So this is the intermediate situation, if you want. One has to say, this has been known since beginning of the 80s. This has come up something also in the 80s. These were, let's say, very exotic animals and exotic ideas before, let's say, mid of 90s, 2000. Okay, so just this came up. Really, the big business of these people do since, let's say, the idea of something. Maybe there could be some stuff which is funny related to neutrino masses, and we try to be a bit off the road, not to follow exactly the conventions which people had in mind earlier. And it gained more and more momentum, where people were finding, like at the LHC, the Higgs boson in 2012, but until now, nothing else. So maybe we are looking not at the right thing. We are not looking, we shouldn't look for the lightest supersymmetric particle. Maybe we should more look for some guys which give neutrino masses. Be more exotic, be more explorative, let's say. Like this was the inspiration for also going in this direction, just roughly speaking. Questions until here? Are you okay? Yes, please. There's also a radiative model for Dirac. You can do even, I'm not sure whether you come to this draw, but you can do even a seesaw mechanism for quarks, for giving masses to quarks. There, Dirac. So I mean, you can do that, but the whole inspiration from inventing different mechanisms for neutrinos comes from the say that they are different nature. They're Marana. So it's not in you will see you are kind of a bit more forced if you want to have a radiative Dirac model, because you have to avoid that you write down the plain tree-level Dirac term, right? If this guy should be leading, you have to first kill the other one. That would be, just to give you an idea. But I would not like to enter in more details because I would like to come to the classical type 1, 2, 3 seesaws. Urgent questions? If not, let's go to 1, 2, 3. Actually, we are not going to discuss 1, 2, 3. We start with 1, then I briefly comment on 3, and then we come to 2. That's more organic. Yes. No, I mean, so there are two things. So we were now saying we start from the standard model, and we don't know what is beyond the standard model. So which means we do an effective field theory approach. Now, once you have made up your mind and you believe in that there's, for example, type 1 seesaw, you just put in the particles which you need in order to do the type 1 seesaw. And then you say like, this is the model, just the UV completion, the ultraviolet completion, which is valid even up to the Planck or through whatever you want. I'm probably not Planck, but you know, and then you say you are happy and you don't do an effective field theory. You say like, I know the answer. I know the exact theory which is there. Obviously, that's something which we discussed very briefly. You can always match this on the effective field theory back. Okay. So which means like you can match a type 1 seesaw back onto the Weimar operator. You actually see this right away. I mean, maybe we can do this very quickly. Without doing much work, you can see this right away. Why do you see this right away? Because we have in front of us the Feynman diagrams. You don't know yet what is all in there, but what you see, I mean, if I have to write down the Weinberg operator as a Feynman diagram, how would you draw that? Everyone. What would you do? Should be meeting some point because there's this Cij over lambda, 2 x's. Okay, we have 2 x's and 2 neutrinos. Yeah, so let's make also the errors right. Probably should go like this. Yeah, 2 x's, the phi guys, and 2 neutrinos. Okay, so observe, please, these Feynman diagrams, the type 1 seesaw. If you actually take this line and you make this line to a point, you get the Weinberg operator. You have done this. I suppose everyone has done this already. Do you know this funny diagram? This is an N, this is a P, this is an electron, and this is a nu bar. What does this describe? How does this look in standard model? Not everyone at the same time, please. So what do I need to do in order to write this in standard model? So in standard model would be something like there's a D, this becomes a U, there's going to be an E out, there's a nu bar, and there's a W, which is, sorry for the very weird wavy line, there's a W boson in between, okay? That's what it is in standard model. And then you have another D, which is flowing through, and then you have another U, which is flowing through because that's going to be a neutron. And in the end here, you have a proton. It's exactly the same diagram. So when can you see the difference between this and this? in the very moment when you are able to resolve, you have a microscope which is good enough in order to look that there's this heavy particle, the W boson, which has 80 GeV. If you have only energies in your theory and in your experiment, which are like 1 GeV or less, you see this. If you go to a collider, you see this. Because you will see that there's this W boson, this new particle, which is propagating, okay? You see obviously also the difference from a theory point of view. This one is an interaction which has 4 fermions and 1 vertex. This is formally dimension 6. This is non-renormalizable. This has at each vertex 2 fermions and 1 gauge boson. Each vertex is dimension 4. This is renormalizable. This is what appears in the star model. This is different. Okay. So, and we are not doing anything different. We're doing exactly the same here. So this works for the type 1 seesaw, type 3, type 2. I mean, many ways of doing. Okay. Just to say, this is not being so. And what does this, what people, theorists would call it, if you go from this theory to this theory, from the one with W boson or without W boson, what are you doing? Actually, formally, you do something which is called, you integrate out the particle. Which means you're only interested in low energy effects. You are not interested in the dynamics of this particle itself, of the W boson, because anyway, you don't see it, you don't have enough energy, you go there. So this is for the neutrinos. You would say, like, I do the same. I can imagine to do the same with the guys here, the right-hand neutrinos. They're so heavy because we were saying category number 1, this lambda is huge. The new particle masses are huge. I don't produce them at colliders. If they have 10 to the 12 Jeff mass, forget it. Even if you are young and you have a long time and people maybe have new techniques and whatever, you're not going to produce these here at Earth directly. No way. So you would say, okay, this just gives me this. So I just integrate it up. Huh? So just to see. And this is the matching which you do from the concrete ultraviolet theory, which gives you an explicit answer to how to generate the neutrino masses, on the effective theory, which just says I have an effective operator. I don't know the exact thing what happens inside here, but still it does the job what I want. I get Majorana masses for neutrinos. All right. So far, so clear? Or problems, doubts? Shall we really now write down the Lagrangian for the type 1 seesaw? Would you be ready for that? Then we go ahead. We have already half of it discussed, so it's not dramatic. So we do everything, so we make our life easy. We do everything first for, okay, we can write it more generally. So we do type 1 seesaw. I said we already have half of it. So we already had this. Right tilde. Okay. So for type 1 seesaw, you introduce a new type of particle, which is called right-handed neutrino, or right-handed neutrinos. The number k we learned has to be minimum 2. And we also remember what are the gauge quantum numbers of this is 1, 1, 0. So these are the gauge singlets. Okay. So this is half of the type 1 seesaw Lagrangian. Can you guess what the other half is? Can you guess? Yeah. How would you write this down? And I should put some opportune indices. What else do I need? Then I write something which I call MR, and then this is K, sorry, K and L. This is Majorana mass for right neutrinos. Majorana mass for new R's. So question to you, which kind of quantum numbers do I violate? Or which kind of symmetries are okay with this, more generally? So do I violate any of the gauge symmetries of the standard model with this term? Yes, no, maybe, I don't care, whatever. I don't know, there can be various answers, these are point of view. Who thinks we are violating any gauge symmetry with this term? Who thinks we are not violating any gauge symmetry? What does the rest think, actually? So we're not violating any gauge symmetry with this term because we said these are gauge singlets, okay? You can write down this combination. We're also not violating Lorentz invariance, but we are definitely violating lepton number. And by how much do we violate lepton number? Because usually you give this as lepton number +1, then the bar has -1. Then in order to get this term invariant under lepton number, you give +1 to the right-hand neutrinos. Then you would get here -1, -1, gives -2. So this is lepton number violation by 2 units. As you would expect, because you make Majorana masses, right? Very good. You mean the Weinberg operator? I mean, actually, you're asking how to get from this Lagrangian to this, or? Yeah. Yeah, but why do you want that? I mean, the question is the other one. So you want to say, I write on and down this and the Weinberg operator, but I forbid this one. All right. But how, I mean, what is your justification? No, okay. Yeah, I understand. But justification, I mean, in terms of logic. Because, I mean, first of all, this term is renormalizable. The other one is not, the Weinberg operator. So I usually have a hierarchy in what I consider to be important. I first write down all the renormalizable terms which I can, and then I go to the next level, which is non-renormalizable, right? The second thing is, if you say like, I really insist on having this and the Weinberg operator, but not this one. Yeah, but then if you really want to have it, do we have a symmetry with a new type of symmetry, which you can invent, which you can propose to have this type of term, the Weinberg operator, but not this one. You see, the point is either, so the principle is either I have a gauge principle, I have a symmetry principle, whatever, and I strictly write down all the terms which I can up to a certain order, or I mean, I can just choose what I like, but this is not the principle which we follow usually, right? The standard model followed exactly this principle by saying, I impose the gauge symmetries, I have the particles, and then I write down everything which I can write down, right? So if you want to forbid this one, you have to say then lepton number becomes a gauge symmetry or whatever, right? Then this is not allowed, but then you also kill the Weinberg operator. At least as it's written there. You can add new particles and whatever. So, okay, but then you change the whole thing again. Is this clear? Other questions? Then I would say, we look at this one. So we said that these here are gauge singlets. So there's no protection from the gauge symmetries for this mass term. That actually says this can be anything. This can be also extremely large. That's the point why people say, if this is a mass for a gauge singlet, this is not protected by electric symmetry, by saying that this should be below this scale or whatever. This can be extremely large. So this could be also 10 to the 15 GeV. That's what we want. And then obviously, as you know already, since this is a Majorana mass term, I should have that this is symmetric. Let me just write this here as reminder. And more, I actually do not want to do at this level, but I want to simplify my life or our life. Let's make our life simpler in order to do the analysis of the type 1 Caesar. We consider only one generation. I know this is not realistic, but let's consider one generation. And let's consider also that this is already after electric symmetry breaking. Okay, if I do one generation, and so I call this L, let's just L type 1, 1. I want to have only the relevant terms which are there. New L bar, new R, and then I have minus 1/2, conventionally MR. Sorry, I chose, I'm not making you unhappy, I chose a different convention. This is new R, C bar, new R. It's the same, it's not changing anything. But just to be consistent with what follows. So this M, D nu we have seen already. This is going to be the Yukawa coupling here times the VEF of this Higgs. This is V over square root of 2. So now this is easy enough. So plus, if you want to be correct, you write everything always plus emission conjugate. Otherwise, the Lagrangian is not going to be real and so forth. So now we do something clever. We would like to write these two different mass terms in the same matrix. So we can do that. So we get a matrix which is this curly M is going to be a 2 by 2 matrix. It's going to sit in a basis which now has new L, new RC, and new L bar. Or does it have? No, it has this. Sorry, I changed the convention. New RC bar. Okay. So why can I write actually these two in the same vector? No, even if it's not my runner, but on very general principles, if you have a right-handed field, or you have the left-handed over charge conjugate, or charge conjugate over left-handed, this is always the same chirality. These are right chiral, both, independent of whether they are my runner or not. Right chiral, left chiral, guys. Okay. Just to say this is consistent to put them in the same vector. You don't put left and right in the same vector because you don't have the right chirality. But these combinations, if you operate with charge conjugation, do have. Okay, just to explain you why I like to write it in this form. And now let's fill this matrix. How does this matrix actually look like? Help me. What can I put? Can I put something in this entry? In this, why not? Okay, I actually would need, we don't have put anything in the Lagrangian which is of this form. So we don't, this gives a 0. Is there something which is here? What is it? Okay, same out. Is there something also on the off diagonals? What is it? It's both times mu d. Because the charge conjugate, the HC, sorry, the HC actually gives me the converse, okay? So now this is a 2 by 2 matrix, which you can diagonalize. I mean, you can, in general, you can diagonalize a 2 by 2 matrix, right? Because why do we diagonalize it now? Everyone, why do we diagonalize this matrix? Why don't we just stop there and say, okay, fine, life's good. We have to find the mass eigenstates. If not, we don't know what are our physical particles. Okay, so you can always diagonalize a 2 by 2 matrix, that's easy. But you make your life even easier by saying that mu d is much, much smaller than mr. Because that was the idea, that the new particles have a mass which is really, really very heavy. So that's the seesaw limit which you take. So that's the seesaw limit. So seesaw limit. Okay, very good. No, I do everything much easier. I just give you the result for the eigenstates and I just say that I will get one which is light. Thank you, Joe. So I leave the hard work, then now it's just to Joe. I get a light mass, which is this. And you trust me for a second. And I get a heavy mass, which is this. I call this M heavy, which is just this. Okay. So you can work this out by yourself. So, which tells me I get out of these two particles one, which is going to be heavy with the mass of this mr. So whatever it will be 10 to the 14 Jeff. And one which is light, which actually has this form of what this is the seesaw, right? This is the seesaw because make this heavier, this gets even lighter. No? So now we actually want to have the eigenstates. We don't want to have the eigenvalues only. We really want to know the states. And if you did the calculation with Joao, then you know actually what the eigenstate should be. And I will write just the result. The light one actually is going to be nu left minus m d nu divided by mr. That's it. And the heavy one is going to be md over mu mr plus the new RC. So, why is this the case? Just by diagonalization. How many degrees of freedom actually do we have? And which was just to discuss again the nature of the particles. With how many degrees of freedom did we start, and with how many particles do we end? So how many degrees of freedom does a new L have? Spinor degrees of freedom? And a new R? And we end up with two particles. So no. Here we have the light one and the heavy one. So we started with 4 degrees of freedom, 2 in the new left and 2 in the new right. We end up with 1 light particle and 1 heavy. They both have 2 degrees of freedom, which means they are both Majorana. So these are 2 Majorana fermions now. So everyone has 2 degrees of freedom here. Okay, this is how they distribute. Now, please help me with the orders of magnitude. So this one should be related to the electric scale, because we said this has this 1 over square root of 2, so this comes always from the valve of the Higgs, okay? Times the so this is around 200 GeV. And the light one, this ml, should have a mass of 0.1 electron volt. This is going to be the one which we identify with the light neutrino, right? So then we can say, okay, we choose the MR accordingly. So for the MR, you will get something which is of the order of 10 to the 14 GeV. Are you okay with that? Because you have this MD nu, you square it, you have to divide by the MR, and you hope that you get for this ML 0.1 electron volt. So you can calculate it, right? So now we have fixed everything, right? We have fixed in particular what this size should be. Now, say, yeah. Mm-hmm. Yeah, you can interpret it like this. You can also say like, look, I have 2 here from the new L, I have 2 there, right? And I get 2 new particles. I interpret this not as a one single particle which has left and right. I interpret it as 2 different particles. In that case, then you're only writing down one. So the current is fixed. Yeah. Then the new L is more lowercase l is left. Exactly. And also the heavy one is left-handed, because I wrote this also with a new L and new RC, because in this basis. But I say it's a different particle. No, it's always a spinor has 2 degrees of freedom. I mean, this is a new L has no. I mean, no. You have 2 plus 2, right? Because you start with new L, which is 2 independent, and new R, which is 2 independent. So if you look at this, actually, now we come to this, you will learn that the little l is mostly the new L, while the little h is mostly the new RC. You see that? And they are independent. Okay? Mm-hmm. So, no. Mm-hmm. They're 2 Majorana. They're 2 Majorana that are not forming one Dirac, because one has a light mass, the other one has a heavy mass. No? No. I mean, no. I mean, the question is, if you have now, you ask the new little L. This is the left. So it's left. And now you ask what is the right component of the new little L. Then this is related to the new little left, because this is Majorana. This fulfills the Majorana condition. The new little L fulfills that this is nu little L C. This it does. Okay? This is what it does. This is the Majorana condition. No?
And it lives on its own.
It lives on its own. Exactly. Exactly. Independent, which have also, we have shown that these are mass eigenstates. They're different particles. Yeah. 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 Exactly.
Then you're applying that. So you're saying, I apply the Majorana condition to u small r.
Mm-hmm.
Show that this is Majorana. So
Exactly. Exactly. And the same I do for the new age. Okay? This is the one. I mean, they are both independent Majorana. And they are not combining to one Dirac. That's usually why you could also write one Dirac as two Majorana, no? Because 4 makes 2 plus 2, and then you combine, no? Because yeah, you're not losing 2 degrees of freedom. No, 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 no. They always say 2 plus 2. I mean, we start with 4. We start with 4. We end with 4. So if you, so, and they combine like 2 plus 2. So we can do a different game. So actually, I mean, no one does this, but in principle, if you don't have a Majorana mass for the right-handed, the mass matrix would be this, right? Can you diagonalize this matrix? It's even easier, just to have fun. What is this? How do I diagonalize? What are the eigenvalues of this matrix? I mean, I asked the question, now everyone, what is the eigenvalues of the matrix, which is this one? Which one? Which Pauli matrix? There are 3, okay? Come on. This has as eigenvalues -1 and 1. Okay? This would be saying that you get this and this. Obviously, it doesn't make sense to say minus for, so you talk about the masses is the absolute value. And what are the corresponding eigenstates? What are the eigenvectors of such a matrix? It's like plus minus 1, and let's say this, okay? No? It's this. So you can interpret now, you can either say like what, okay, 100% of the people say this is a Dirac neutrino, which has a nu L and a nu R independent component. You could be also crazier saying like, these are 2 Majorana particles which have opposite CP parity, which are these combinations, and I can interpret them as 1 Dirac. It's the same. The same, I mean. Yeah, I mean, it's like, no? I mean, this is the same, I mean, it's a, you can now write this is a different basis, right? It just the same. I mean, it's the thing is only the matter of what you now identify as physical degrees of freedom. So these things you identify as the same particle, which have, I mean, components with opposite CP parity, which combine into 1 Dirac, which you can really throw again into 1 Dirac with 4 components. And if you have a mass difference of 12 orders of magnitude or more, they are not just the same components of, I mean, of the same, no. They are 2 different particles, but then 2 Majorana.
This is why we say that we use Majorana to be able to
I mean, the point is, here in this picture, this funny picture, where you have all these sorts of ways of generating neutrino masses, there's only this one, which is Dirac. Okay? Why is only this one, which is Dirac? Because it's hard to forbid this. If we now talk about why in construction you would resort to Majorana in order to have different ways of generating masses. I mean, it would be, if you want to have something exotic to generate masses for neutrinos which are Dirac, you have to first forbid this one on basis of symmetries, which is always otherwise there. I mean, this is going to come from this thing, right? I mean, forbid it before you are allowed to think about an alternative mechanism. And you see here, you would do it actually by introducing some new symmetry. You probably don't see it, but I do see it because I know that there has to be a new symmetry inside. Otherwise, the vertex, this would be also allowed. Well, for Majorana, the story is completely different. I mean, for Majorana, the story is different. You have a new type of symmetry. You are breaking lepton amber. Because then you have the way of having thinking about which is the source of lepton amber breaking. I don't introduce arbitrary many. I introduce one usually. I introduce the Majorana mass for the right-hand neutrinos, or I introduce this little mu here for this inverse or whatever. Okay, and then the circus starts, as you were saying. Okay, good. Sorry for the deviations. May I just come back after these funny exercises here? I hope you are with me by saying that these are two separate particles, this little new L and this little new H, and they are both Majorana. Yeah. Uh-huh. Yeah. We come to, no, yeah. We can make out of these numbers, we make matrices in the end, okay? But I would like to do one thing first. So I want to understand how much new L and new RC I do have in the little L here. So can you tell me what this ratio actually with the numbers which we have here? What's the number standing here? We've seen 200 Jeff, and the other one is 10 to the 4th. So what's the order of magnitude? And so here's probably a minus 10 to minus 12, okay? For here is the opposite. There's a 10 to minus 12 standing here, plus, so, okay? This says, actually, what I interpret as light neutrino is really the one which I know from the standard model. This is the one which sits with our friends, the left-handed charged leptons, in the same doublet. What is the heavy guy is really this new thing which I just added. Yeah? It's very well separated because this is the seesaw again. This mixing is extremely tiny. They are not doing crazy things. They are really extremely separated. So, and each of them is 2 degrees of freedom. So that they have 4 in total again. Is this okay? Good. And then we come to your question. We have the problem that there are 3. There are 3. Okay. You do the same circus for the 3. And you actually, instead of having the little matrix which I wrote down, you have a 6 by 6 matrix, and then you do the seesaw for 6 by 6. And in matrix form, the light neutrino mass matrix. So this is now the light neutrino mass matrix. Is this? So now this one is 3 times n. So these are the number of new R's matrix. This one is the inverse. So you have seen before, we always had the mass formula for the new L is going to be the m little l is going to be m nu d squared divided by mr. So now I mimic this little thing here, which is in numbers. So, okay, you do it formally, but you recognize that it's similar if you now write it in matrix notation, because you have 2 times the m nu d, and this one you now get as inverse. And this is an n times n Majorana matrix if you want to do the general thing. And this is the transpose. So why do I have to have this form? Because this is also a Majorana mass matrix, right? Now light neutrinos are Majorana. And what we said, Majorana masses, the mass matrices, we feel that they are symmetric. Okay, I actually, even without doing the computation, you could kind of guess that this must be the right form. Just by dimension and by knowing that the structure has to be symmetric, which is due to Lorentz. I mean, the fact that they are fermions and Lorentz, the anti-symmetric part drops out. So, and this is type 1 seesaw formula for 3 generations for light neutrinos. And I can throw in n generations of heavy ones. As we were saying, n is minimum 2, but could be, if you want, can also be 100, but then the matrices get kind of big, but that's your problem. That's not mine. Just to be honest, it's yours, not mine. And then we understood this one here, okay? Shall we still, I mean, we are already much over time, but shall we still continue another 15 minutes? Is that okay for you? You can also say no. I appreciate just an honest answer. If you say no, it's fine as well. Are you good with another 15 minutes? Okay. You are very kind to me. Then I would like to jump to the type 3 seesaw. The type 3 seesaw actually is the same incarnation as the type 1 seesaw, but it just has a bit more fun. So this is the, now I mean, this right-hand neutrino is boring. It's a total gauge singlet, so this really boring. So let's say, try to have a bit more fun. So we start with LLI bar phi, and so you remember when you do the type 1 seesaw, you write a new R here. Is this the only possibility you have? So now we start again. The LL has as gauge quantum numbers 1, 2, minus 1/2. If I bar it, it has 1, 2, minus, plus 1/2. The phi has 1, 2, 1/2 is the Higgs. If I twiddle it, it's 1, 2, minus 1/2. So what is this? This is actually a 1, 2 cross 2, and a 0. What is 2 times 2? I mean, not 4. In SU2, please, okay? So this is 1 and 3. The 1 we use, this is the right-hand neutrino. Okay, let's do the 3. What does it mean? You will get something, you write something here, which, oh, it's written sigma r. Sigma r is going to be a fermion, or fermions, because usually we have, also these like to come in more than one, as again a coupling. This is a fermion, or fermions that have 1 and 0. No color, no hypercharge, but now they are SU2 left triplets. What does this mean that they are SU2 left triplets? Everyone, what does it mean? Do they talk to, I mean, does this guy talk to a photon? Now, this is actually a bit a tricky question already. Does this guy talk to a W boson? Let's start with the easy one. Because now we actually wrote down 3 particles at a time, okay? We wrote down something which is going to be, now let's see the convention, something like, I think it's plus, 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 and 0. Huh? We wrote down this. Because we wrote down a particle which has 3 components. Okay, so this is a fermion which has 3 components. And you see actually this guy talks to W plus minus, it talks to Z, it also talks to photons. So it's not as boring as a neutrino right-handed, right? The nu R, which is 110, who cares? So this guy really has more fun, usually. But this guy, so now the next question to you, since you're experts already, can I write down a Majorana mass term for this guy? Yes, no, maybe, I don't care. Are possible answers. Can I, can't I? Yeah. Can I get a gauge singlet? If I do 130 cross 130. This actually is, this is the question. So I do the 1 and the 0 and I say, yes, I can. So you do the SU2 left 3 times 3. What is what is 3 times 3 in SU2 left? So it's 1, 3, 5. So this is symmetric, anti-symmetric, symmetric. It has a singlet, so I can do a 1, 1, 0. Okay, I can do with this. I can write down without destroying anything a gauge invariant Majorana mass term for them. And I can do this in the same way as I did it for the. Looks like this. Now get some Majorana mass, which is sigma KL 1/2. It's also symmetric because it's a Majorana mass. So KL is LK. And then the same circle starts, okay, just to stay in the picture. Because what do I change? So now this is the fantastic thing of a blackboard. You just do this. Number of right neutrinos becomes number of sigma r's. The same. This is the only difference between type 1 and type 3. So, and diagrammatically, you see exactly, it's a copy. Yeah? It's not, they didn't do a writing mistake. It's really the same story. Yeah. Yeah, I mean, you have more fun. You have more problems also because they talk to gauge bosons. They influence many electric precision things which we know. So, yeah, but that's why people also thought like maybe more fun. This just boring, more fun. Okay, so this is the alternative, right? Mm-hmm. Mm-hmm. Yeah, something very antipathic to most people, but very nice actually.
Each of them has each of the sigma 0 plus and plus plus are just replicas with 3 different mass values, or
That's a good question. Whether they do, I mean, usually these things actually are much heavier than, I mean, you take them heavier than the electric scale, otherwise it would have been found. And the question is, what would split their masses? But they split their masses can only be something which is related to electric symmetry raking, because they start to sit first in the same multiplet, right? If you want to take them away from each other, you have to kind of get in the WEF of the Higgs, okay? And if you make them, I mean, assume that this Majorana mass, let's say, this is 10 to the 14 Jeff, because I want to explain the light neutrino masses nicely. Okay, do you care about that this is 200 Jeff heavier than this guy? So, I mean, just to... if you have this one as the dominant term, the electric splitting is it's not that relevant, right? It's not the dominant player, right? If you come down to lower scales, then obviously the spectrum gets more complicated, but then you also have the problem if you split them too early, they will do, I mean, as you know, they can do electric position stuff. Yeah. Yeah. No, I mean, they were said, I mean, no, yes, of course. I mean, they were, I mean, no, okay, but let's come back. Okay. We're talking about LHC. We are not talking about super whatever collider. I mean, where does the LHC end up? I mean, 13 TeV, right? Okay. What does it tell me? I can at maximum test 13 TeV. If I'm nasty and I say, okay, but I would like to have light neutrino masses that are naturally explained, I take this 10 to the 10 minimum, 10 to the 12 Jeff. I mean, I don't care about your LHC. So, I mean, if you bring it down, if you are willing to accept that this coupling is small, this can be lighter. You can still do the sort of seesaw. This is lighter, then you see them potentially. Or you have even not even direct effects, but you have even indirect, like electric position. Then the story starts. Yeah, sure, sure, sure. Yes. I mean, all sorts. Also, charge lepton flavor violation, they do bad things. I mean, these ones are not innocent as a right-hand neutrino. No, they are not just, they like to have their own couplings to W boson Z, and I mean, they do things, no? They have a rich, very rich phenology. For example, the Phenon group at IFT with Bell and Gavella, they were looking into this, or also here in Italy, Carla Biggio was looking into this thing. No. I mean, this can be very interesting. You can also say like they can be nasty because you can bound them in various ways. No, I mean, they are more active. They have large, I mean, they have, without relying on any coupling to left-handed neutrinos or left-handed guys, they have their own way to talk to the standard model, because as you say, they couple to gauge bosons. We know that G, SU to left coupling is not small. Yeah, perfectly agree, yeah. You have many more opportunities to kind of search for them, bound them, but I mean, bounds are anyway, I mean, TeV-ish, no? They're not 10 to the 10, Jeff. Other questions? Otherwise, we come to something called type 2, but actually has different topology. Type 2 is different. Type 2 is different because the particle which we add is not yet another fermion. Remember, right-hand neutrinos are fermions. These sigmas are also fermions. But we could also add a scalar. So where does the difference come from? You see it already at the level of the Feynman diagram. So what's the characteristic here of these two Feynman? If you have to describe it to someone who's unfortunately blind, what would you say? What's the characteristic? Huh? Of this one and of this one. Which particles are coupling to each other? So the characteristic is you have here two vertices, they are the same. A left-handed particle couples to the Higgs, left-hand particle couples to the Higgs. It's always this LL bar, this. Yeah? This is because roughly you can write the Weinberg operator. Now this is very badly written as this. Yeah? But if you think in terms of the Weinberg operator, you can also reorganize them. You could say, maybe I have something which is this, and I have another one which is these guys together. And this is what the diagram up there in the middle does. Now you have hanging two left-handed lepton doublets at the same vertex. This means by counting the dimension, this is 3½ plus 3½ This makes 3. So you don't couple another fermion to it. The only, I mean, you could couple a gauge boson, but okay, it doesn't have. The most easy thing you can couple to it is a new scalar. Here's called delta. And then you have to see, can I also couple it here? It turns out to be yes, I can also couple it here. So let me write this now, not in this, let's say manga style, but let me write it in a serious theoretician style way, which means we have a delta, we have a Yukawa coupling, which now is called Y delta, I J, L L I sigma. I need I sigma 2 in order to couple, I mean, just the nice SU2 structure I want to expose, or maybe to most of you not that nice, but anyway, I don't care. This is the I sigma 2. Oh, downstairs looks better. I sigma 2, delta dagger, I, and then I have Hermitian conjugate. And this delta is what is called the Higgs triplet. This is a Higgs triplet. This has gauge quantum numbers, as everyone has gauge quantum numbers. And we can compute them. This is 1, 2, minus 1/2 for the LL. The LL C bar also has this. We get this twice. What can I couple to here in order that this is invariant under gauge symmetries? You find out that this is 1, 3 plus 1. Yeah. And then you do what you are obliged to do. You please write down every term at the renormalizable level at least. In your Lagrangian, which you are allowed to write down by gauge symmetries, okay? And then you find out when you come to the coupling with the Higgs, you're allowed to write down this term. Okay. So, first of all, let me just say, this guy, obviously, since it's a triplet, and the SU2 left has also 3 components. And I think I have here made some, wait a second, sorry, I take it back. This should be plus, 0, and minus probably, because this one is convention is plus, plus. I'm very sorry, plus and 0. Yeah, we have always, for the triplet, you have a doubly charged, a singly charged, and a neutral component. So, again, you add one new type of particle, this time a scalar. It has 3 components, so in that sense, you add at least 3 particles. Now, may I just ask one question to you before we go on with the analysis of the lepton number, and then we are also we are finished. How many of these do you think you need in order to get the neutrino masses which we observe? Why? No, here actually theory is nicer because the structure of the diagram is also different. And these couplings here are all independent. Obviously, they have to be symmetric in flavor space, but they're independent. They're not like this problem which we had before that you have otherwise a matrix which has a smaller rank. Here, you always have a 3 by 3 matrix. This is always a 3 by 3 matrix. Independently of how many of these guys you have, you can have, if you have 2 of them, you will get 2 3 by 3 matrices, right? So actually, the minimum number of X triplets you need in order to generate 3 light neutrino masses which are non-zero is 1. So, but you can say it's more economic in this respect if you take the type 3 seesaw where you have the fermion. You see, you need 2 fermion triplets for the Higgs triplet. 1 is enough, but just because it's different topology, it's the structure here, the coupling is totally different. No, it's not. And let me. Are you okay with that? Let me go now to the analysis of lepton number. Who can convince us that we can't define lepton number in a consistent way? So let's say we start with the first term. Can I make this invariant under lepton number? Yes, no, maybe, I don't care. I don't know. It's always these options, right? So this one has lepton number plus 1, this one as well. So does this break already lepton number? No, you could say, okay, I define the lepton number of delta as being -2. Okay, this -2, this is 0, fine. So, but now we made a choice. The delta has lepton number -2. Now we go to the second term, which is also there in the Lagrangian. So this is like a pi square delta. So the Higgs convention has lepton number 0. Okay. Now we made the choice, the delta has lepton number -2. Bad luck. Delta L is equal to 2. So you break lepton number by 2 units in this way, because having these 2 terms, you break it. Maybe you now say, okay, you have been very stupid. You should have started not with a term with the LL, but you should have started with a term with the Higgses. Okay, I start with the term with the Higgses. They have 0. Then, not to break lepton number, so the lepton number of delta is also 0. Then this guy is happy. Then I go to the LL C bar LL. This is +1, +1. Now I have the delta here. I made my choice. It's 0 now. Okay. Delta L is equal to 2. Okay, I've not been that stupid, because either way I do it, I necessarily break lepton number by 2 units, which means now all the alert goes on. I will generate lepton number violating stuff. Yes, I will in particular generate Majorana masses for neutrinos. Okay, very good. So now you want to know the answer. What is the mass actually looking like? The mass is extremely easy if you look at that. There are 2 we just do the usual thing, what you learned, I mean, what Fermi did, okay? We just say, we look at this diagram, so the diagram in the middle, and we integrate out the delta. Because we you know, with these couplings which we have, you can write down this diagram, okay. So we integrate out the delta, which means we first take into account all the vertices which we have. So we have this vertex which has the two new lefts and the delta. So this is this y delta. Then we say we integrate out a scalar particle. It looks very much like integrating out W boson. Just get the propagator. Okay. So now what do I miss? I miss the coupling which sits here. This is the one to the two x's, the mu delta. And obviously, then the two x's get a VEF. So square, you want. Then it's also, is this okay by dimensions? Sorry, one question just to you, not that you are completely fall asleep. Is this okay by dimensions? Can this give me a mass for neutrinos? Yes, no, maybe? So this one is something like GV square. So the coupling is 1. Then we know that the f of the Higgs is GV, then auto square. So now we have to look, this is a new type of coupling. I think maybe you have never seen this before. But here, that's important. You have two Higgses, the two phi's and the delta. So this is mass dimension 1, mass dimension 1, mass dimension 1. This coupling here, which sits here, is not just a number. It has a unit. Okay, just this is important. This has also mass dimension 1. So this means there's also, I mean, unit GV or maybe more electron volt. So this is okay. So this is for the mass dimension is okay. If you do it correctly and you take into account that this should be a Majorana mass, usually you don't put the factor of 1 over square root of 2 is not there. So you would get the y delta divided by the m delta square. You get the mu delta and the v square. This is the formula. Taking into account the convention of the factor of 1/2 with the Majorana mass, this is the usual one. So this is type 2. So, and then we talk about, with Joa, you were talking about hopefully 2 things. Is what else this, now this is the question now you as an experimentalist ask. What else can this delta do? I mean, not as the sigma, no? I mean, it's not innocent. It's not innocent because also this is a triplet and has to left and it even has Hyperjudge. And even more so, it has this funny coupling to 2 left-handed lepton doublets. It does this. And you will look with Joao in terms of things of all these processes like mu2,3 and this thing that it does as well, in principle. So the other thing which I wanted to say about this delta, which is not innocent, is, so why do we stop at type 3? 1, 2, 3, we have seen 1 and 3 are very similar. Now 2 until now stands alone, right? Is there another option to have a type 4? Also this you discussed then with Joao, why there is no type 4 schizo. Okay. So yeah, this was a very long lecture. Sorry for that. Was it clear? That's the important point to me. Was it okay for you? Could you follow? Was it too theoretical, too crazy? I mean, you will have a chance to have a few examples with Joao as well and discuss more in detail also your questions. Feedback is always appreciated. Is there something which you say is no, I mean, totally lost, or I don't know, or you just want to have coffee? I mean, I also understand this perfectly. That's a legitimate request. I mean, I have the same, to be honest, but no, I mean, I hope it could become like the idea of why we go this way in order to generate neutrino masses. What are the thinking behind in order to arrive at these different ways and even many more? And these three ones here up there are like the classical ones, which I think everyone that just has something to do with neutrinos definitely should have seen once in a life, and also appreciate why we do that, why we use them, why they look as they look. Okay, that's the point. Here, this probably, I mean, also very important, but probably, let's say, for the beginning, in particular for the experimental, this is the part where we theorists have fun. Okay, this is the part where it's here we have fun. Okay, in many ways, we have fun. For example, because instead of just having this, can have this. I mean, just we have fun. I mean, in many ways. Sorry for for that. I think I just stopped before you. Now everyone lose confidence in all theorists and say, "Oh my God." Yes. Thank you very much.